Hey YouTube, this is A Sphincter. Today we're going to talk about the Sytrus and try to unravel the mystery of FM synthesis and get to the bottom of how this matrix works and what the hell is happening with FM synthesis anyway and all the crazy mathematics behind it. Now, in order to do that, first we have to understand a few basic things about FM synthesis. Every FM synth that I've worked with, every good one anyway, has a matrix. Whether it looks like this with knobs or whether it has to do with a different graphical representation doesn't matter. They all have to do with using certain waveforms to modulate other waveforms. Now, these operators here all have a distinct waveform shape. You can see down in the box, could be a square, could be a pulse, could be a triangle or sawtooth, doesn't matter. What you have to understand about these is that they're not necessarily sounds. Alright? They can be simply used to imprint a shape or a pattern into another sound without adding its own sine shape. Now, that's kind of confusing, but I'll try to demonstrate it as best I can. First, what we'll do is we're going to work with ring modulation. Now, ring modulation affects the amplitude or the volume of a wave. Frequency modulation affects the pitch, because pitch is frequency. So, this is Edison here. We're going to record on input, and we're going to listen to an unmodulated. Let me unmodulate that. We're going to listen to an unmodulated sine wave in the key of C. Sounds like this. Yep, and that's pretty much what we'd expect to see. This is, when we zoom in, we'll see that's the sine wave pattern. It looks identical to the pattern we see here in the operator 1 box. Now this matrix here, if you think of it as going from left to right, it makes a bit of sense. What this would indicate would be that operator 2 is affecting operator 1, but operator 2's individual sound is not actually going to come out. This would indicate that operator 3 is affecting operator 1. Okay? From left to right. And this output right here is going to indicate that operator 1 is going to make its way to your speakers. Alright? If I did this, this would indicate that operator 3 is going to make it to our speakers clean. If I did this, that indicates that operator 3 is going to be affected by operator 4, and that output will go to our speakers. Get it? Alright. So, back to our unmodified sine wave here. Whoops. Looks like this, sounds like that. What we're going to do here is do some basic ring modulation. I'm going to use a very slow sine wave to modulate the amplitude of our initial sine wave, and it sounds like this. Sorry, sounds like this. Now that's a pretty easy thing to see here. We can see that not only is it a sine wave up close, but when we zoom out, there's a very distinct sine wave pattern impressed upon it. Right? Now let's do the same with a triangle. This is a triangle wave, and we can clearly see that a triangle shape emerges. With a sawtooth, we get a strange diamond shape. With a square, we get nothing. With a pulse, we get an occasional popping noise, not much. Other strange shapes you can get by adjusting the tension, you will see them very clearly represented, much as you would expect to see if these patterns were simply combined in the amplitude. And that's pretty much what's happening. We're taking the shape of this right here, this operator. We're not actually listening to it. We're not listening to this sound. We're simply using the shape to impress a different amplitude pattern onto our first initial sine wave. So the sine wave is always the sound we hear, the volume of which is only determined by our second operator. Is that confusing? Shouldn't be. It's pretty easy to see right here in front of our eyes. Now, FM is an entirely different animal here. FM synthesis is about changing the pitch according to one of our operators here. And it's not so difficult to understand, but it's a bit more difficult to visualize. And the only way I can really think about doing this is just to play it a few times here. We'll work with another C. This will be a frequency modulated sine wave. we're going to go full modulation. But the sine wave that I'm using to modulate is, in fact, let's see, it's only 1/200th of the speed. Sorry, it's difficult. So if our initial frequency was 660 hertz as a C, our modulator frequency would be 3 hertz. Okay, so we should see a difference pretty apparently, and we can hear a difference. Now, when we look up close, you really can't see the difference. Only at certain levels can you really see the difference, and this is just sort of a bad frequency here. It's not easy enough to see. So I'll speed this up to 1/20th of our initial speed, and here we go. Now you can hear that. When we look up close, we'll see that it still remains a sine wave all the way throughout. It just has different frequency sort of ups and downs through it. You have high pitch zones and you have very low pitch zones. Alright? Now, if you remember the shape that our ring modulation produced, having these sort of ups and downs throughout, they would exactly match up in timing with this sort of shape right here. And the way it actually works here, it's a bit difficult to visualize, but if I draw an envelope across it, our secondary operator, which is our modulator here, is going to look a lot like this. Sort of just tracing a sine wave at roughly this tempo, roughly this position. Now I know it looks a bit confusing because what you would expect to find that when the frequency or when the modulator is high, the high pitch zone would come out, and when the modulator was low, the low pitch zone would come out. That would indeed make more sense, but unfortunately it doesn't happen that way. FM synthesis relies on the value of the slope. Okay? It does not care about the actual position of this waveform, and I can prove it to you. Watch. If we just eliminate all this, and we'll record a triangle. Let me fix my tension here. We'll record a triangle wave. Sounds like this. Okay. If it were based on the, how do I say it? If it were based on the position of the wave, we would get very smooth ups and downs, but instead we get very strictly alternating bands. Okay, you see that what's happening is I'll zoom in. You have one position when it's moving downward and the slope changes, and you have another position when it's moving up and the slope affects the frequency. Okay, that is the way FM synthesis works. Okay, another example is if we go into the square, if we go into a square zone or even a sawtooth. If we do it with a sawtooth, it produces no modulation. Why? The reason is because the slope is consistently downward. See, it does not care about the actual value. It cares about the slope. It cares more about the shape, which is why you'll typically see very bizarre and strange looking operators when people are producing FM synthesis. You'll get something that's just completely off the wall, really hard to reproduce, hard to imagine, and it produces all kinds of varying degrees of different sound effects and so on. So that's almost impossible to predict, but when we look up close, yeah, you can sure see that our modifier is impressed upon our frequency of the sine wave, and only in a few spots does our initial sine wave actually come out. Alright. Well, that was a mess of a noise. I didn't care for that one at all, but it was just a good example of how these operate on each other. This frequency multiplier will give you a frequency which is based on whatever key you hit on the keyboard, basically. I'll have to do another chapter on this because I'm out of time. Thanks for watching. I hope you have a better insight onto how Sytrus works and FM synthesis in general. This is Ace Pinkter out.